Hello, judging committee. We are team 1098, and we are doing problem C. Our team consists of Clara Place, Charles Fraga, and myself, David Lincoln. We are from Rose-Hulman Institute of Technology. Our coach is Dr. John McSweeney, also from Rose-Hulman Institute of Technology. The problem that we selected, problem C, is about Fritz the dog. Fritz is a golden retriever with an apparent catching problem. We were provided many videos of Fritz failing to catch several types of food. We have set out to determine if those thrown foods are physically uncatchable or if Fritz is clumsy and he's missing catchable throws. To make this determination, we have modeled both Fritz and the foods with a set of differential equations. In this problem, we had two distinct modeling sections, one for Fritz the dog and the other one for his projectile food. For his food, we tracked his trajectory using various starting heights, starting velocities, and starting velocity angles. For Fritz, we built him out of a simplified model using linkages. We applied geometric physical constraints to the linkage model to represent the dog's mobility. To link both the ball and the dog's trajectories, we added a head linkage onto Fritz that tracks the ball's movement and checks whether the ball is caught or not.
We broke this problem into two major systems, the food and the dog system. To start this, I'm going to talk about our modeling process for the food. Our first major assumption is that we assumed air resistance is proportional to the velocity of the ball squared. This is a fair assumption, and you'll see it pop up a lot in aerospace applications. Similarly, we also assumed that lift is proportional to the y velocity of the ball squared. A slightly more shaky assumption that we ended up making is we assumed that the food is translating exclusively in the xy plane. This means that the food is not rotating, and we don't have to deal with anything like the Coriolis effect that would turn this into a 3D dynamics problem. Ultimately, we decided to do this just because we thought it would get rid of any unnecessary complexity and make the solution process happen a lot faster for us. To actually go about solving this problem, we decided to utilize the rate form of conservation of linear momentum to develop a representative dE in the x and y direction. We then would numerically solve that dE utilizing Simulink. So looking at the equations we generated for the food item, for this we just kind of assumed it was a meatball. Looking at our free body diagram, we assume that the force of lift is acting directly up and the weight force is acting directly down. Once again, that lift force is proportional to the rate of change of the y displacement squared. And we also assume that it's going to have a drag force that's going to be affecting the acceleration in the x direction at a rate that is proportional to the x velocity squared.
To begin modeling Fritz, we had to simplify his body into a usable linkage system. We began by saying that Fritz is modeled as a 5-bar linkage system. We had 3 fixed-length straight bars, which represent his hind legs, his back, and his front legs. It's important to note that in our model, we do account for these 3 bars to have both mass and moment of inertia. We also have 1 linkage to represent the ground, as well as 1 variable length bar that allows his front paws to move up and down during his jump. We do also have a 6th bar used for the model of his head. However, this bar does not impact the movement of any of the other limbs in the system. This slide shows our simplification of the 5-bar system that we will be using to model Fritz. This diagram also shows the different notation of the angles and links that we will be using to derive our equations in the following slides. This slide shows our free body diagram and kinetic diagram for one of our 3 fixed length links in our dog system. As shown, we use path coordinates, which is a normal component, which is along the member, tangential component, which is orthogonal to the member, and so as the member moves, these 2 directions will change as well, and then a 3rd direction, which is orthogonal to both of the other 2 directions. As shown, at points D and O, they're pin joint connected, where this link meets our other 2 links. We also have a moment applied at point D, which is where the dog's hips are, which we will discuss in the following slides. From these 2 diagrams, we can generate 3 equations, one for summing the forces in the normal direction, one for summing the forces in the tangential direction, and the 3rd from using the conservation of angular momentum rate form to find these 3 equations for the link.
Fritz the dog is a generally complicated system, so we had to make many assumptions to model him correctly. Some assumptions that we made are that Fritz's limbs are modeled as rigid linkages and have fixed lengths. To model his jump, we also assumed that Fritz applies an impulse with his front paws and that he pushes directly upwards. We said that Fritz can control the movement of his torso by generating a moment in his hip. This moment is calculated using a proportional controller. To do this, we created equations using conservation of linear momentum and conservation of angular momentum. We used Simulink to solve this system, and based on the food's trajectory, Fritz uses kinematics to guess how much impulse he needs to apply to the ground.
In order to restrain the dog's motion, we looked at literature to try to find minimum and maximum angles for different joints. We found that Fritz's back leg is limited to 90 to 144 degrees, his hip joint is limited to 97 to 124 degrees, his front leg is limited to 107 to 155 degrees, and Fritz had a maximum gape angle of 44 degrees. Next, we combined our two models in order to get results. Our approach was that Fritz's head linkage is constantly tracking the food. In order to do this, we made a few more assumptions. First, we said that Fritz's head has negligible inertia compared to his other body parts. We also said that if the food enters a polygon defined by the maximum gape angle of his mouth, the food is considered caught.
This is an example of Fritz actually catching the food that's thrown at him. As you can tell, it takes him a couple seconds, and then he applies that upwards impulse to get him launched up. After that, you'll notice that gravity kind of starts to drag him back down. This is another example of the dog catching the ball. In this scenario, we have the dog, or the ball is launched with a little bit extra initial velocity. So this gives the dog a little bit less time to respond, but Fritz still ends up catching it in this simulation. This is an example of a case where our simulated dog is not able to catch the ball. Because our dog can't translate, when balls are thrown with a really steep angle or at a greater height, the dog sometimes just can't get in a position where it will ever be able to put the maw in line with the ball.
The graph on this figure shows a meatball with different forces of air resistance acting on it. As you can tell, that while the air resistance is about 2 times or below the nominal amount of air resistance, the overall behavior of the ball doesn't really change. And both of these are still very catchable for Fritz, or for our dog in the ideal model. However, as soon as we hit anything above 3 times the nominal air resistance, the overall trajectory of the ball is altered so much so that the throw is no longer far enough for the dog to easily get the ball. This means, because our model of the dog is not actually able to translate, that all of the 3 times, 4 times, and 5 times are uncatchable for all circumstances for this dog, unless we toy with the initial position of the dog. After watching the videos, we noticed that, generally speaking, the dog jumped when the food was at the peak of its arc. So we decided that the dog had, between the time of the peak of the food's arc to the time when the food hit the ground, to react to the stimuli. Generally speaking, we assumed that the dog responded immediately to its environment, and it did this by generating a moment at its hip that was proportional to the angle of deviation. Essentially, this acted as a sort of proportional controller, in that it is just a constant gain multiplied by an error term. Because this behaves like a proportional controller, it responds very terribly to any sort of phase lag, and this moment actually becomes very detrimental when it has a sort of time delay or a response time delay in it. And because of this, we cannot catch the ball at all if we have any sort of response time delay. This is a major issue with our model.